So again, the first slide set is going to be 10-1. The second one that I'll try to cover today is going to be 10-2. They are all posted. Both of them are posted on titanium. Talking about here failure, when it comes to failure between flexure and between shear, this is going to be a standard flexure failure, if you like. And you see here the big tensile stress, which is a principal stress here, is going to be in this direction, the horizontal direction. So usually the crack is going to be perpendicular to the main stress direction, which is the tension direction. So when it comes to shear, I'm sure that you guys are aware of that the fact that usually this shear is what we call here diagonal shear is going to happen on this angle. Most likely it's going to be mainly on 45 degrees in most cases. And you see here, this is going to be the direction of the tension. This small box here is going to be the stress element that you guys have studied in the past in the mechanics of materials. And this give you direction of the tension force or the main principal stress, if you like. So here's going to be the same thing. This direction here is going to be the principal stress direction. Here is going to be also the principal stress direction, the main one, which is the tensile one. If you look here for this also beam, this beam failed in shear, and you see the direction here of the principal stress also is going to be in that direction here. So when you have two principal stresses, the first one, which we call here stress number one or sigma one or F sub one, is going to be mainly the tensile stress. The other one, it could be either compression or maybe low tension. So the main tensile stress is going to be in this direction. Same thing, another beam tested here in shear. The principal stress here is going to be in this direction. The other principal stress, this is going to be here sigma one, this is going to be sigma two. So sigma one is going to be in this direction, which is the larger value when it comes to tension force from the stress. So we understand here the meaning for the shear stress and strain. If you take here the stress element, the standard one that you guys have studied in mechanics of materials. So the stress element here is going to be 1 by 1, could be an inch by an inch, a foot by a foot, millimeter by millimeter. The shear stress is going to be on both faces. So this one here, we call this tau xy. This one here, we call tau yx. But they're going to be equal to each other. This is the reason this slide here, it says that this is going to be tau xy, which means both of them is going to be the same. If one direction is going to be going up in here in this side, which is the x side, the other one needs to be going down. Otherwise, the stress element is going to be unstable. So to make it stable, if this one is going to be going up, this one is going to be going down, so that this is going to be exactly equal in value to this one. Same thing for the x direction. The x direction stress, which means the y face of the stress element. If the top here is going to be going right, the bottom one has to go left because you'd like here to do summation of the forces. And the force is going to be equal to stress multiplied by 1 because the stress element dimension is going to be equal to 1. So the force in the x direction is going to be balanced out. If you take the moment about this point here, you find out that this shear stress multiplied by 1 is going to be equal to the shear stress multiplied also by 1. Therefore, the shear stress in both directions, the x and y has to be equal. By applying the shear stresses on a stress element, you should expect some distortion of the element itself. It's going to be doing this. So the stress here is going to be called tau xy, and the strain is going to be called gamma xy. Now, the strain here is going to be happening in both sides, in both directions. And as you see here, this gamma xy is going to be actually an angle of rotation. So what happened, this 90 degrees now becomes 9 degrees subtracting gamma xy. One half of this gamma xy happens here, and the other gamma xy happens here. Looking here at the stress-strain relationship between the shear stress and the shear strain. And the y-axis, we're going to be doing here the shear stress. On the x-axis, going to be the shear strain. The relationship between the stress and the strain in the elastic range is going to be given by this equation. Tau is going to be equal to the modulus elasticity, the shear modulus multiplied by gamma, the shear strain, which means the shear modulus here is going to be equal to the stress divided by the strain. It's going to be equal to the y component divided by the x component. And this is what we call here the shear modulus. Relationship between the modulus elasticity and the shear modulus can be given by this equation. G, which is the shear modulus, is going to be equal to E divided by 2, 1 plus nu. This is actually the Poissons ratio. For steel, the shear modulus is roughly 11,000 KSI, and the shear modulus is 29,000 KSI. And we end up with nu, which is Poissons ratio, is going to be equals to roughly 0.3. For steel, the same ratio here is going to be equal to roughly somewhere between 0.15 to 0.16. So let's say 0.16 for steel, for concrete, and 0.32 or 0.3 is going to be for the steel. Here is one of the beams that you'd like to study. It's going to be the location of the stress element. If the stress element here is going to be taken at the neutral axis location, it means there is no stresses on both sides. I'm talking here about both sides, both faces here, which means the stress in the x direction is going to be equal to 0. Reasons because when the stress element here is going to be extremely very small in height and in length, let's say 1 millimeter above 1 millimeter, it's going to be very small. Effectively, the stress in the x direction here is going to be equal to 0. You end up with only shear stresses throughout the entire stress element. Now, with this stress element, if you put the shear stresses on both sides, now you'd like to figure out the result of these two forces or these two stresses, you're going to have a diagonal tension on both sides like here. Meaning, if I'm going to go back here, if I take the stresses here in these two directions, I'm going to end up with a resultant going up. It's going to be pulling the force here, and the same thing, I'm going to have a diagonal tension. It's going to be in this direction, which you are looking here at. Now let's apply this to an actual concrete beam with some cracks after testing. This is the reason that I'm expecting your diagonal tension to happen in this direction at nearly 45 degrees. The other components going to be coming in this direction. To resist the shear stresses and the shear forces, the best way is to have these stirrups or ties to take the shear. I understand that the force, if I'm going to go back here to the previous slide, the force is going to be actually at 45 degrees roughly. So adding some ties here is going to be helping to resist this diagonal tension. If I'm going to be adding here some ties. The tie spacing is going to be S. Usually the stirrup or the tie cross-section area, we call this A sub V. So A sub V is going to be the total cross-section area of the vertical legs of the tie. So if you take the cross-section area of this plus this, it's going to be called A sub V. Now looking at the principal stresses, try to understand this sigma 1 and sigma 2. I'm taking here you back to mechanics of materials. General stress element is going to have all of the stresses, all of these components. You're going to have a stress on this face is going to be sigma x, stress on this face is going to be sigma y, and some shear stresses. What you can do here, instead of cutting this stress element on this, we're going to say straight direction, which means this face is giving the x, this face is giving the y. You start here to rotate the stress element when you cut the section, when you cut the stress element, on an angle that we're going to be calling here theta. With this angle rotation, you're going to find out that the stress is just changing. The amount of tension that you have here may increase a little bit or reduce. If one of them is going to be going up, one of the stresses here in the x direction, which means the tension stress or normal stress, if you like to call it this way, one of them is going to be going higher in value, the other one is going to be going lower in value. At a certain point, the shear stress is going to vanish. It's going to have no effect at all. At that point, we're going to call it the principal stress direction. So the principal stress direction and the principal stresses is going to be those stresses that at this point here, as you see, that there is no shear stresses at all. It's going to be all normal stresses, and the shear stress is going to vanish. We don't know the exact angle, and this angle you need to determine this angle if you like to do detailed analysis. Roughly in concrete, it's going to be at 45 degrees in our design or analysis in most cases. It's going to be close to 45 degrees. Now, once it happens, you're going to see here that you have the maximum tension stress is going to be in one direction. The other direction is going to be either tension or compression, but the amount of tension is going to be much less than that of sigma 1 direction. And there's not going to be no shear stresses at all. At this direction here, it means that you reach the maximum tension force that can happen at an angle. And this is the reason actually that we have this shear failure in concrete beams, if there is no ties at all. To find out the principal stresses, you can use this equation. So sigma x and sigma y is going to be the stresses in here that you're taking when you take the stress direction before rotation. Once you rotated, now you'd like to figure out the sigma 1 and sigma 2 in terms of all of the stress state. And you have this equation that you guys have studied in the past in mechanics of material. Sigma 1 and 2, as it says here, 1, 2, because you have here plus and minus. So if you like to find out sigma 1, you do the plus. For sigma 2, you do the negative. For the angle, you can figure out the angle based on this equation. Tangent of 2 times the angle is going to be equal to that. Any questions so far? Any question so far? No? We're good? All right. Now also we studied Mohr circle. Mohr circle, the one that we saw for mechanics of materials. And with any given angle, you should be able to figure out the set of stresses. How do you do here, the Mohr circle? Just as a reminder, quick reminder. Here is the main or the general stress element with all the stresses on it in terms of normal stresses in both faces and some shear stresses. On the x-axis, we're going to put the normal stress, sigma. On the y-axis, we put the tau, the shear stress. Now, next to that, we try to figure out 2 faces. So we say we need to plot here 2 faces. So each face is going to have a point on the circle. This is going to be one face, and this is going to be the other face. In this face here, we have combination of 2 stresses, sigma and tau. In this face also, we have 2 stresses, sigma and tau. Sigma again is going to be like the x, and this is going to be the y component. And here, this is going to be the x, this is going to be the y component. So the y component here is going to be the shear stress. X component is going to be normal stress. So someone's going to say, you mentioned here, you're just pointing at this and say this is going to be the x direction. Yes, x direction would come to the stress itself because the stress sigma y is going to be plotted here in this direction. Don't forget, x direction is going to be for the stress, normal stress, y direction or the y axis is going to be for the shear stresses. Here's the first phase. It's going to be phase A or point A. Here's point A. What happened at point A? I have a stress of sigma x and a shear stress of tau. So normal stress sigma x and shear stress is going to be tau xy. So here's the first point. How do you plot it? X component on this graph is going to be equal to sigma x. Y component, which is tau xy, is going to be this stress value or this value. With that, you plot here point A. So with that, I was able here to plot point A on the stress diagram. The other face or the other point on the same circle is going to be point J, which is this point here. The stress value in the x, which means on this x-axis, the stress value, sigma y, I was able to plot it here. It's going to be sigma y, x component on the graph. The y component is going to be equal to the shear. And look here at the shear. This shear here, I'm going to be calling it negative shear. This is why it goes to the other side. So negative shear is going to be negative tau xy. Now I have 2 points on the circle. The center of the circle is going to happen once this line connected between the 2 points is going to intersect with the x-axis, which means this point here. I guess I should be able to figure out the coordinates for this point, because the coordinates on the x-axis is going to be equal to sigma x plus sigma y divided by 2 is going to be 1/2, which means the average of these two stresses. So I said, okay, let me draw my circle. Here's the circle. This circle here represents, if you like here to draw any line, it's going to be running through the center. It's going to be all possible combinations of stresses if you like to rotate this stress element to any angle. I said, okay, good. How can we do this? Now looking for the principal stresses. Principal stresses give you these two stresses when there is no shear stress at all on the stress element. No shear stress at all means that you're going to be right here along this line, because in here the shear is going to be equal to 0. With that, you're going to have two stress values or two stress for the combinations. You're going to have one value right here and the other value is going to be right here. This one here is going to be the maximum tension, which means sigma 1, and the other point here is going to be sigma 2, the other point. So in some cases, both of them is going to be tension. Some other cases, this one's going to be tension, the other one's going to be compression. This one will come to concrete design and concrete analysis. If you're doing other analysis, you may have both of them is going to be compression, to be on the other side. This provided that you have compression, like a case of hydrostatic pressure, or you have compression pressure coming for all sides when you started the analysis. So this one here is going to be called sigma 1 again, and this one's going to be called sigma 2, which means the two principal stresses. So whether you do it with more circle, or if you may, let me go back here to the previous slide, one of the previous slides. This give you this slide. You can do it with the equation, you can do it analytically, or you can do it with this more circle if you want to, whichever is easier for you. Now understand the meaning of the principal stresses, and we understand that this is going to happen at a certain angle, and this angle most probably is going to be very close to 45 degrees in concrete beams. The maximum shear stress, it can happen on another angle. Here's the maximum shear stress. If you take here this vertical line is going to be intersecting with the circle at 2 points, the top and the bottom, and with that you're going to have here tau max on both sides. We're not interested in this tau max, we're more interested in this principal stresses. Now what's going to happen, we're going to take two stress elements as A1 and A2 in a beam. One of them is going to be in the bottom, which means A1, and the other one's going to be in the top, A2. And let's just assume that this beam, this is not a concrete beam, this is going to be a homogeneous beam. It can be wood, it can be steel, you name it. The bottom one here is going to be exposed to compression in the x direction. How do I know this? If you draw here the stress distribution of the normal force in the x direction, it's going to look like this. Compression here is given the top, the bottom is going to be exposed to tension. Which means A1 in the x direction is going to be exposed to tension, and A2 is going to be exposed to compression in the x direction. In the y direction, it's going to be very small. The amount of stress, if you take here this stress, multiplied by the width, which means 1, it's going to be very small compared to the value in the x direction. So we should be able to ignore the vertical stress coming from this loading. The shear stress distribution is going to look like this. I'm sure that you guys have done this before. I guess if I may still remember the equation says tau equals, supposed to be tau equals, this is going to be equal to V times Q divided by I divided by A, if you remember the equation here. Based on this equation here, you should be able to figure out the stress distribution of the shear. In the top and bottom, there's no shear stresses at all. right in the middle, you're going to have the highest shear stress within the depth of the beam. This gave you like detailed analysis for the shear. If you like, there is a simpler way of doing this. It's not going to be exact. If you just take V divided by A, if you take this cross-section area, take the shear at this section here, take this V divided by this A, is going to give you this value here. It's going to be like an average shear stress. The ratio for rectangular section of this maximum shear and this average shear is going to be 1.5. We call this the shape factor that you guys have studied this in mechanics of materials in the past. So my job here, since I'm going to be taking this for A1, is to draw a section here and then figure out the amount of normal stress on the X face and the amount of shear stress, which I can take from here. So after I do the stress distribution for normal stress and shear stresses, I can figure out the amount of normal stress at stress element A1, and the same thing when it comes to the shear. I can also repeat the same thing when it comes to stress element A2. All right. Here is the stress element A1 has been taken at the bottom. We should be able also to figure out the principal stress in this case. But look at this stress element. There is only shear stress and tension stress at the bottom, and here's more circle. In the top one, you have the same stress element, but instead you're going to have compression and shear stresses. And for both of them, you should be able to find out the principal stresses. Here's the equation for the flexural stress, the very common one that we have used, the famous one, the standard. And this is going to be for the shear stress, tau or V lowercase, VQ divided by IB. V is going to be the amount of shear force at the section. Q is going to be the first moment of area at the height given. I is going to be moment of inertia. Beam is going to be the web width, which means in this case it's going to be this beam width, B. Okay, good. To find out the principal stresses, I guess I should be able to use these two equations. These two equations is going to be the exact two equations that you have seen in slide. I guess it was number 14. It's going to be the exact same two equations. Okay. Just a reminder here, the load combinations that you guys are familiar with. Now, we'd like to see here what the code says about shear design for concrete beams. So you have the load factors. With the load factors, you should be able to figure out V sub U. After you find out the demand, which means V sub U, now we need to figure out the shear strength. Shear strength here is coming from two components. It's going to be the concrete strength and the steel strength. The phi factor is going to be standard of 0.75. Again, you have contribution of the concrete, contribution of the steel. For the concrete, contribution is going to be equal to 2. You have here a factor of 2, square root of F prime C, the width of the web times D. Okay. Maximum value for square root of F prime C is going to be 100, which means maximum of 10,000 psi. Recall this value. I want you to remember this value. We're going to be talking about it in the second slide set, about this 100. Square root of F prime C is going to be equal to 100 max of psi. As you see here, the concrete strength, when it comes to shear, is going to be based on the interlocking of the concrete aggregate and particles. Now, the steel component, the steel trends component, or the trends coming from the steel due to the steel presence, is going to be given by this equation here. AV is going to be the cross-section area of the vertical legs of the tie or the stirrup. FYT is going to be the trends of the ties. D is going to be the depth, effective depth of the beam. S is going to be the tie spacing. According to the code, the maximum steel strength contribution will come to shear is going to be equal to 8 square root of F prime C. which means for this any given section, you're going to have maximum of 8 coming from the steel and 2 coming from the concrete. You have a maximum of 10 square root of F prime C when it comes to the shear strength for a concrete beam. Once you go above 10, you cannot really use the concrete beam anymore with the given dimensions. And in this case, you need to change these dimensions, which means maybe you'd like to increase the width or increase the depth of the concrete beam. Because as given here, once you go beyond this limit, the steel cannot really take more shear than 8 square root of A prime C. If the amount of shear demand is less than 1/2 of the concrete strength capacity, if this VU is going to be less than VVC divided by 2, in this case, you don't really need any ties. But once the shear is going to be going above this limit, which means 1/2 of the concrete strength when it comes to shear, you need to provide minimum amount of ties. You have here 2 equations for the minimum amount of ties that you need to provide. Two equations. The first one says 0.75 square root of F prime C. Of course, it has to be in PSI times BW, the width of the web, times the spacing divided by F sub Y. Everything here needs to be in PSI. Otherwise, you're going to be receiving here weird numbers. Second equation says 50, the width of the web, times S divided by Fy. Now, when you have 2 minimums, you're going to take the larger of the 2 minimums. Shape of the ties. They have to be closed ties. They need to be anchored on the top and the bottom. So you need to have rebars on the top and rebars on the bottom. Otherwise, it's not going to be acting with you. It's not going to be triggered when it comes to shear strength with steel. We have a quick example here. It says determine the shear strength adequacy for this beam. They give here the beam center to center span is 22 feet. The clearest span is 20. If you guys recall here that when we take the critical section for shear, it used to be a D distance from face of support, which means face of column. This is why it is important to understand how much is the clearest span, so that we're going to go D distance away from this face of support and figure out the shear demand. Dead load is given as 1.5 kip per linear foot, and the live load is 0.7 kip per linear foot. Concrete strength is provided. Yield strength for the steel is provided. I have number ties, and the spacing is given as 14 inches. Bottom steel is not that critical, but what I really care about is going to be the tie and the spacing. Based on this equation here, if I may go back a couple of slides, A sub V that you have in this equation, when you have number 4 ties at 14, A sub V is going to be equal to 2 number 4. Why 2 number 4? Because I have 2 legs. Number 4 is going to be 0.2 square inches. I have total of 0.4 square inches for A sub V. S here is equal to 14 inch. Like in this equation, S is equal to 14 inch. D is going to be the effective depth. This is H. Effective depth is going to be equal to H minus the cover minus the tie minus 1/2 the rebar size, the rebar diameter. And with that, you're going to have the T. F sub Y for the ties, as given here in this example, is going to be 60,000 PSI. Let's see the solution for this example. In the solution here, I have the demand, dead load, and live load. I can do the load combinations, 1.4 versus 1.2, 1.6, ended up with this 2.92 kip per foot. This is going to be the shear, the load demand, uniform load on the beam, 2.92 kip per foot. Here's the beam, here's the span. Center to center is 22 feet. Clear span is going to be 20 feet. I have the ultimate load is going to be 2.92. I need to figure out the shear demand at face of support. At face of support is going to be right here. I can call this the reaction if you like. So you can take here 22 divided by 2 times 2.92 to give you here 32.12 kips. This give you the reaction. The shear at face of support is going to be here face of support because this is going to be the clearest span. It's going to be equal to 20 feet times the ultimate load divided by 2. You have here 29.2 kips. I'm trying here to develop the shear diagram, right? So the first value here at the center line is going to be the reaction. The second value, 29.2, is going to be the shear at face of support. The one I'm interested in is going to be a d distance away from face of support, this red line. And here's the reason. The code allows me here to take the critical section for shear to be a d distance from face of support. If you like, you can do interpolation and find out that the shear demand at d distance away from face of support is going to be 25.9 kips. Excuse me for a second. And right at the critical section for shear, which means at d distance, you can do interpolation, find that out to be 29.9 kips, or you can simply reduce it by the depth d. The depth d here to be 13.5 inches. You can divide this by 12, 5 to 10 feet. And then you say here the shear demand at d distance away from face of support is going to be equal to the shear right here at face of support 29.2, subtracting this distance, which means d distance, 13.5 divided by 12, multiplied by the uniform load 2.92. So in this slide here, I was able to find out the shear demand, which is at d distance away from face of support. Yeah, second. All right. Now the shear trends, I have the concrete contribution and the steel contribution. Concrete contribution is much simpler than the steel. You take here the phi factor of 0.75, and then you say 2 square root of f prime c. F prime c is going to be 4,000. The section dimension is going to be 10 inch by 13.5. Now everything here is going to be in psi. To have your answer in kips. And why do I need to have it by in kips? Because the shear demand here was given to me in kips. Again, divide here by 1,000, I have total of 12.8 kips. This gives me the shear capacity. Demand is 25.92. So it seems that I need some steel because the concrete itself cannot resist the shear demand. What is given to me here in the problem, it says number 4 at 14 inch ties. So what I would do here, I'm going to take number 4, 2 times 0.2, times 60, f sub y, times 13.5 inch for the depth, divided by 14 inch for the spacing. And with that, I have additional 23 kips for the resistance of the steel. I cannot use the whole 23. I can use only 75% because the phi factor here equals 0.75. Meaning that at the end of the day, I'm going to have total trends of 12.8 plus 17.36 come from the steel. So this gives you the concrete contribution. This gives you the steel contribution. I have total of 30 kips, roughly. 30 kips is going to be more than 25.92. Therefore, this concrete beam adequacy, this beam is good when it comes to shear. Any questions? Please. Hello? Anyone here?
Yes, we can hear you.
All right, great. How it is 13.5? All right, 13.5. Let me go through this. You have 16-inch, subtracting. Let me just add all the deductions here. It's going to be 1.5 plus number 4 tie. Give additional ½ inch. Now I have 2 inches, 1.5 plus ½ inch, plus additional ½ inch because number 8 has a diameter of 1 inch. So I have 1.5 plus quarter plus half. This is going to be 2 and how much? I can roughly say 2. You have 1.25, 1.5 plus half is going to be 2.25. Let's say 2.5, roughly. So with 2.5, you have 16 minus 2.5 is going to be 13.5. This is how I came up with 13.5 for the depth. Did I answer this question? Great.
Did you calculate the effective? Am I right?
Yes, this is the effective. Yes.
Yeah, thank you.
Yeah. Any other questions? All right, good. Minimum reinforcement. I need also to check the minimum reinforcement for the shear. What happened here? The demand is more than 1/2 of the shear strength by the concrete. You're going to say, yeah, it is more than the concrete strength itself. You have here 25.9 versus 12.8, which means that you need to have a check on the minimum steel needed for the tiles. This is the reason that I have these two equations. As you see here, everything here is going to be PSI. Concrete strength is going to be 4,000. Yield strength is going to be 60,000. Section width is going to be 10 inches. The spacing is 14 inches. And here's the 0.75. This is not a phi factor. This is just a constant in the equation. With that, I need 0.11 square inches. Another equation here for AV minimum, if you run it, you're going to be getting here 0.12. What we have provided is number 4, and I have 2 legs, so I provide here 0.4 square inches more than 0.12, which means I'm good. I was able to cover the minimum needed. Okay, diagram. Here's the diagram, the shear diagram. This is the shear diagram from the previous slide. It shows the 25.9 kips, which is the critical section shear. The shear demand is giving the other values. Here's the column. Any shear within the concrete width itself is going to be taken by the column, which means this section here is going to be the column, right? The column is going to be here. So all of this is taken by the column. You don't have to worry about it. And here's the critical section of shear. This section also, you don't have to worry about it. Why? Because the code says you need to go at the distance away from face of support and start to look at the shear, which means all of the shear in this box is going to be taken by the column and this hunch, by this piece. So you don't have to worry about it. Now, if I take the shear here and draw a straight line for VVC, this is going to be the concrete strength only. Let's provide that I have only concrete. All of this shaded section of the diagram is going to be taken by the concrete only. And everything that you have here on the left-hand side or within this box is going to be taken by the concrete and the hunch and this piece. This blue triangle is going to be whatever that you are resisting here by steel. This is going to be the shear resisted by steel. You need to cover this triangular shape or triangular shape of this diagram by the steel. This makes sense. Now what happened to our pre-stressed beams? All of this was just about conventional concrete design. The big question is what happened here when you have pre-stress? Are we going to be using the same equation? Do you think concrete strength is going to be larger because the amount of pre-stress that you put on both sides? I'm going to say yes. Concrete strength itself, PVC, is going to be going up because this compression that you put on both sides is going to be closing all the cracks. So most likely, this section of the beam is going to be free from cracks. Same thing here. The section that you're going to see, maybe in some designs, you're going to see some cracks and pre-stress is going to be maybe this section here. And the good thing about this section, this is going to be the section with high shear forces, because the shear force is going to be high here, it's going to be high here, it's going to be almost equal to 0 at the middle. So actually this pre-stress is going to be helping me with PVC. I said, okay, good. What else? Also this balanced load. What does it mean by this balanced load? All of this balanced load is actually reducing the amount of shear demand on my beam. This is going to be the reality. This balanced load, because once you start here to put this pre-stress, you're going to pushing this with a load of W. And this WB, the balanced load, is going to be subtracted off this W. So the effective shear demand is going to get reduced, which means the shear that you want the beam to resist is going to be equal to V, which means this V is going to be the demand coming from the diagram, the shear diagram, subtracting V sub P, which means the shear strength or force or vector, as it says here, coming from the pre-stress. If this makes sense to you. You remember this equation here for the stress distribution. If you take this equation here for the stress distribution, and then you have the top and bottom, and you try to figure out the principal stresses. You remember the principal stresses for more circle or for even the principal stress equation? You're going to have here some major tensor stress is going to be coming in this direction, which means a diagonal tension. Now, what was the direction of the diagonal tension if I may draw it here on this beam? Say diagonal tension is going to be coming this way. It's going to be coming like this. Other diagonal tension is going to be coming like this. About the crack direction, you see the crack direction is going to be like this, if I may make it longer. And the crack direction, the other side is going to be coming like this. We go here to some of the beginning slides. Just imagine if this had been a pre-stress beam. So the pre-stress cable is going to be coming this way, which is good. You see where's the direction of the tension force? It's going to be coming like this. Just going in the same direction, which means this pre-stress strain that we put here is going to help in the shear. Number one is going to be closing all these cracks. It's going to be increasing the interlocking between the concrete particles. Number two is going to be taking some of this forces that we were talking about. Whatever is left, we're going to be taking it by ties. And the design for the ties is going to be very similar to what we have here in our concrete design, conventional concrete design. So we're going to end up here by using these equations. Let me go here to these equations. This slide, we're going to be using exactly the same slide when it comes to the steel design for the ties in pre-stressed beams. Any questions before I start the second slide set? Maybe I'd like to give you 5-minute break and then we continue. Any questions? All right. Go back in 3-4 minutes. All right, let me start again. So in this slide set, I'm going to be doing the alternative design method only. And this happens when FPE is going to be more than 40% of FPU. Generally speaking, FPE, when we do our design, when we use here 150 KSI, for 270 KSI strands, we're going to be at 0.56. So are much more than 40%. So definitely we're going to be using the alternative design method. It means I'm not going to be covering the detailed design method in this slide set. Now let me start here from the beginning. The slide that I'm going to be putting my check mark on it is going to be, here's the first one. It's going to be the second one. After this, I'm going to be jumping to slide number 12. Here it is. I'm going to put this check mark on it. So what happens is that the concrete strength is not going to be equal to 2 square root of prime c, and that's it. The equation is going to be slightly longer. The equation here says VC is going to be equal to B times D. This is going to be the cross-section area exposed to concrete. It says here, instead of using 2, I'm going to be using 0.6 square root of A prime C. Conventional concrete, of course, this lambda is going to be equal to 1. So here's the first main difference. Conventional concrete, I have 2 square root of A prime C. And here I have only 0.6 for the concrete. And then I have additional component. This component here, because this equation is going to be in psi, it says here 700 VU, which means the shear demand at the critical section, multiplied by the depth to the pre-stress strains, divided by M sub U. This M sub U is not at the middle of the beam. This is going to be at the same critical section of shear, which means this V sub U and M sub U is going to be at the same section, at the critical section of shear.
No, is it at distance D, the same the moment at distance D?
At distance, yeah, it's about distance D. Let's say yes.
Yeah.
It's going to be a critical
The
section.
moment is going to be the
Yeah.
same distance D. Okay.
Yes. So it's going to be the shear and the moment is going to be at the same location, exactly at the same location, roughly at D. But in pre-stress, it should be at H. And H is going to be the total depth of the concrete beam. So difference here, there's another difference between concrete beams, conventional concrete beams, and pre-stress concrete beams. In conventional concrete beams, we take it at D distance from face of support. In here, you can take it all the way to H distance. Difference is going to be a few inches, couple of inches, but this is how the code is written. So when you look here at VU divided by M sub U times DP, what factor do you expect? I'm just thinking here. It says here that you need to keep your eye on this factor. VU times DP divided by M sub U, it has to be less than 1. So what happen, let's say if it's going to be equal to 2 or 3. All what you need to do is just use it to be 1. So it has a maximum value of 1. So you can say VU dP divided by M sub U max is going to be equal to 1. In most cases, it's going to be more than 1. You do your analysis, multiply by dP. Don't forget that this is going to be all in inches, right? So this dP is going to be in inch because this equation is going to be also in psi. This 700 is a big number. When you think about this equation here, say it's 700 is going to be a big number. Why? Because the maximum square root of V prime C is how much for shear? Based on the code and the conventional design for concrete, it's going to be equal to 100. If you recall this issue that I said, keep it, you'll need it. Which means 7 times 100 is going to be 7 times. So you have here a factor of 7. Correct? Which means this equation here is going to give you a very high number when it comes to the shear strength of concrete. It's not going to be just 2. It can be maybe 6 or 7 or 8 easily, just for the concrete, because of pre-stress effect. You have a minimum value. The minimum concrete strength is going to be equal to 2 square root of V prime C. This is going to be the equation, very similar to the previous one that we use in conventional concrete design. And the maximum is going to be 5 square root of V prime C. And this is going to be for the concrete only. So in our conventional concrete design, we say shear strength is going to be equal to 2 square root of V prime C. In pre-stress, we say it's going to be ranging between 2 to 5 based on this equation. And in many cases, this is going to be controlling your design. So instead of just having 2, we're going to be making it as 5. Very big improvement in strength. If you like, yes, I'd keep this, use this. Let's give you the shear diagram, which is a straight line. And this gives you the concrete strength based on the equation. So this equation here is going to give you this curve. If you need more steel, of course, you add more steel. But you have limits. You see this curve here, it has two limits. It goes from, it should be this based on testing. It goes from 2, not 1.7, 2 to 5. So the range here, I'm going to be also adding this for you here. In the code, it says this is going to be 2. In your book, shows some analysis and says going to be 1.7. No, I'm going to change this to 2. So the range for this curve, the curve which means this curve here, starts from 2 all the way to 5. So conventional concrete design, I'm going to put it back again. Conventional concrete design, I have this equation. 2 square root of F prime C. This gives you the shear strength, and this gives you the shear factor, 2, just 2. And here is going to be a range from 2 to 5. It's going to be this range here. Above this, you're going to be using steel. This is the reason in many pre-stressed beams, you don't really need any shear reinforcement. You just put the reinforcement or the ties at the end for the end block. So here's my equation. Give you like the curve, and they have a range between 2 to 5. How about the reinforcement? What happened if I don't have enough reinforcement? What should I do? Right? I'll add some. So I need this line, which means if the shear demand is more than VC after I use this limit of 5, and after I use this equation, if I still need shear reinforcement, I'm going to be adding it. This is exactly the same as a conventional concrete design. So, I mean, you know it, you have studied before, so you know what's going on. So I'm going to put this check mark on it. How about the spacing for the ties? The spacing for the ties give you very similar, it's give you the same. Here's S max. S max based on the condition. So, okay, I'd like to use this. This is here a flow chart. It says you need to have all of this information. Here's the fee factor. Do you have the FPE is going to be more than 0.4 or not? If you say no, you're going to go to the detail. If you say yes, you're going to be going here. So I need this here. This is all what you need to know. Here's the equation. This is going to be the two limits, 2 and 5. And this is going to be the maximum for this factor. VU dP divided by M sub U is going to be maximum of 1. You just use this. So, okay, good. Are you guys following? Any questions? All right. Good. All right. So what is this slide? This slide actually explanation of this. So this is exactly taken from the textbook. This is exactly what it means. You may need this or you may not. Just gonna put it there. It doesn't hurt. Detailed. Do I need detailed? I say no. We're gonna be doing the alternative. We're gonna be doing the easy method. We're gonna be skipping this. The alternative. This is the one I want. Have you seen this before? Yeah. Just explanation what you see here in the slide. It's gonna be the same. How about this one? S and AV, and have you seen this before? You can say yes. This is gonna be how do you design for the reinforcement. And here is the slide that you really need. Like the steel design for the ties and the stirrups. So we have it here. This is all taken from the conventional design. It's gonna be the same as this. The same as this. Same thing. VS, the strength of the steel, if you need to. All right, this is our example. This example starts at page 23 or slide 23. So, okay, I guess you guys have seen this beam before. It is our only beam within our toolbox, it seems. So familiar with the beam, you know exactly how many strands. If you remember that with 13 strands, 17 half-inch wire strands, and you have all the information. We have the dead load, we have the live load, we have the span, we have the whole thing. And also we have P sub E. So, okay. You should be able to figure out V sub U. And here's discussion on where do you take it? Where do you take the critical section? Look at this. It says here that the code, the 318, allows you to take it at distance h/2. All right? So this gonna be here 40 inches, you take it at 20 inches from face of support. But here, in this textbook, he just decided here to go 1/2 of dp, just to be consistent. So it's gonna be up to you. Do you wanna use this number here, 36.16 divided by 2, or do you like to use 40 inches divided by 2? It doesn't matter. I personally just go to h/2. I'm gonna be doing my design here for the project. Just gonna go here h/2. Now, finding out here, here's f sub PE, and here's 0.4 of FPU, just to prove that it's gonna be okay to use the alternate method. And they said yes, it's fine. It's gonna be the equation I need, so I need to put check mark. I forgot to put it here, and then here I need it here. Then I need it here. It's gonna be our equation that I've been talking about, right? It's gonna be 0.6 f prime c plus 700 bwdp. Here's the range. I have here a max or a minimum and a maximum. It's gonna be my range, right? I'm gonna try here to find out this m sub u at d distance. So you find out the moment demand at the critical section of shear, and also find out the shear demand at this critical section of shear. And then you say v sub u divided by m sub u times dp. As you see here, it's gonna be equal to 1.96. Usually it's gonna be more than 1, which means just use this to a limit of 1. So this factor here that I have in my equation is gonna be equal to 1. I put here this. So you look at this, right? I'm gonna be using 1. Okay, so what's next? I need this slide. Next, find out the minimum VC, minimum concrete strength. It's gonna be based on a factor of 2. I have it here. How about the maximum? Based on a factor of 5. I'm gonna say here it is. Based on factor of 2, based on factor of 5. Find out the concrete strength. So what do you do after this? Okay, now let me try my equation. Which equation? I'm gonna say this equation here. I call this to be my equation, VC equation, right? 0.6 square root of prime C plus 700 times D times B. I'm gonna do it here. 0.6 times 5,000. It's gonna be my equation, the shear equation here, right? This one here, it gives you 161 kips. Your maximum is 76. Your minimum is gonna be 30 kips just for the concrete strength. So if this had been conventional concrete design, you'd use only 30 kips or 31 kips. Because it's gonna be pre-stressed, they're gonna be using this 76. So actually the one at the end they're gonna be using is gonna be this value here, 76 kips. Now compared to the demand, how much is the demand? Do you need any steel? Answer is yes. Here is V sub U. Yes. To answer you, yes, I need some steel. So what you need to do is to provide some steel for the ties, and this is gonna be very similar to any conventional beam. Any questions about the difference now between shear design for pre-stressed versus conventional? No questions? You're good? Now with that, I'm done with this slide set. Yeah, very good example. I'm gonna post it with this markups including the check marks and the whole thing. So if you like, also you need to have this. This is going to be the steel design, very similar to the first slide set that I put there. That's it. You don't need to go through this example because it's going to be based on detailed method. I don't need that. Okay. With that, we are done with the course, all the course materials. There's going to be one thing left for the same beam that you have. You need to do shear design. Should be very simple. It's going to be due this May 7th. So what does it mean by this design? It means that you need to find V sub U, the critical section of shear, and then find also M sub U. And then you try this equation here. For sure, this value here is going to be controlling your design. If you need ties, you can add ties. And you have two good examples. You have this example here, and then you have the other example, which is slide set number 1, if you want, which is right here, 10-1. How do you add the steel? How do you add VS and the calculation that you guys have taken in concrete 1? Should we keep this this submittal here to May 7th, or do you want it to be earlier? Because on May 7th, I'd like to conclude. I'd like you to post the whole thing. So if you like what's going to happen for all the submittals, now I'm sure that some of you now would like to change some stuff in the first submittal, the second, and the third, and this is going to be your chance. So what I'm going to do, I'm going to open a box on Titanium so that you can upload your work, and it's going to be also due on May 7th. When you upload your work, I'm expecting here that I'm going to have for each group, it's going to upload the whole thing all together. As if you like to start from scratch. If you have anything that you'd like to change to earn a few points here and there. So please be sure that you put the best that you can do here in your submittals, and please you upload it by the 7th. So what I'm going to do here, I'm going to send an email to everyone indicating that the submittal for the whole thing, including, the final submittal is going to include all submittals that you submitted before. I'm going to open a special box for it on Titanium. On the 7th, I'd like to discuss with you what you're going to see in the exam. It's not going to be that tough. You guys, you have gone through the whole thing, and it should be simple. You take it at home. You shouldn't have a problem. And also, you're going to be allowed to use your spreadsheets. So you have all the tools you want. Yeah, when you submit, it's going to be 1 per group. Yes, all the slides, I'm seeing here lots of comments coming very fast. Yes, this lecture is recorded. I'm going to post it. This is true. The slide set, I'm going to save it. I'm going to post it as is with all the markups, so you know exactly which ones that I marked up. Yes, it is recorded. Yeah, 1 per group. All right. Any questions before we go for tonight?
I have a question about previous lecture. Can you please 9-3? So the one we did today. The project for. So I do not quite understand the analogy for the. Could you please bring slide number 18? Yeah, this one. So I was just my team, my group member, they were trying to explain it to me, but I still cannot get this M sub C and M sub P.
You're good with column 1, right?
Yeah, I'm good with forces and everything. Column 1, column 2, 3, 4, but not 5 and 6. I'm good with column 7 too.
This gave me the moment coming from what? From PI, right?
Yes.
So where's PI? Let me look. Here's the PI, right?
That's the PI, yes.
Good. Now, if you see here, in the first 3 lines, you have zeros.
Mm-hmm.
No contribution coming from here at all. How's that? It means that you cut a section right here, right? Let me just say that without looking at the lines there, you'll be cutting a section like this. Look at all the bottom forces coming in the concrete, coming in the pre-stress and the concrete and the whole thing, and take the moment about that. That makes sense? So when you take the section here, you take the moment about this section. So how many forces you have? You may have 1, 2, 3, 4, or maybe 5 forces, right?
Mm-hmm.
Each one has its own arm, and with that, you're going to be finding out the moment. And this
Yeah, why is that 0? That's my problem.
no,
Why?
it's not going to be 0. You're going to have a value here for the concrete, but you're going to have any values for this, because when you cut, and then you look down. So there's no contribution from this force unless you start to go above it. So if you're right there, right, your moment arm to this force is going to be equal to 0. I don't know, it doesn't make. Does it make sense?
Yeah, on the level of PI is 0. I understand that.
Okay.
Okay.
Let's say when you take the moment here, you're going to say at PI, there is no really moment come from this one, right?
Yes.
But how do you do the moment? Do you take the moment for all of these forces?
Yeah.
This force here?
That's 0. That for
No.
yeah.
If you take the moment for all the forces, it's going to be equal to exactly 0. Why? Because you're going to have some forces coming this way, some forces coming this way. You end up with 0. The moment's going to be exactly equal to 0 because the moment from the top is going to be the same as the moment from the bottom.
Yeah.
Right? Okay.
Mhm.
So when you cut any section, let's say I'm going to be cutting a section right here. Right here. And we're going to be looking at the forces right below this. You either look in the top or you look at the bottom. You remember when you have a beam, simply supported beam, and let's say that you have column here and a column here, right? How do you find out the moment at this section, let's say? Here. You cut the section here, and then you take all the loads on the left-hand side or the loads on the right-hand side, and then you find the moment for them. Am I correct?
Yeah.
Okay, exactly what you do. When you cut the section, you look either right or left. And here, when you cut the section, either that you look below or above the section. Now take the moment for all of these forces, right? Below that section.
Okay.
This piece of I is not doing anything.
Mm-mm.
Are you good? No.
Yeah, I don't know. Yes, I
Okay.
will go.
Just,
Yeah,
just
this will
consider.
okay. This will give us the moment for
Here's
fifth.
beam. Here's our beam. Okay.
Okay.
Here's this horizontal beam. And you have forces on the beam. You have force come from the top, and one
Mm-hmm.
big force come from the bottom, like this, right?
Mm-hmm. Yeah.
This section only. Now, do you know how to do the moment diagram for this?
Yeah.
Now take this force times this distance. Let's say here's a section that I'd like to figure out the moment for, right? Take this force times this, plus this times this, plus.
Yeah.
Or let's say if I like to work on this section here, I have the option either to look on the right or to look at the left. In their case here, in this solved example, when they cut any section, they look below, which means on the right side. As long as the section is going to be on the right side of this PI, this PI has no force at all. It has no force in the schedule, which means it does not create any rotation or any moment. It's only after the section is going to go above it or to the left of it, according to this, right?
Right.
Okay. Question from Andrew. Yes, please, you need to resubmit the whole thing again. Even if you submitted already, I'd like to see the final submittal in the best way that you'd like to see it.
Thank you.
No problem.
Okay.
All right. You guys have a good night and good luck, and please sign out. if you may. Thank you.
Good night, Professor.
Yeah. Good night.
Bye.